Yes, good afternoon everyone. Good afternoon one and all. Good afternoon to Honorable Secretary Sir, Principal Madam. Good afternoon to Convener Sir, Co-Convener J. Krishna Sir, and our today's resource person, Dr. Sreejith Sir, and also good afternoon to our beloved faculty members, and also good afternoon to all the participants from all over the country. So, it is my immense pleasure to introduce today's speaker and resource person, Dr. Sreejith Sir. Dr. Sreejith Sir has graduated in Electrical and Electronics Engineering from the Nurul Islam College of Engineering. He obtained his master degree in the Power Electronics and Drives from the MEPCO Secular Engineering College, Shivagasi. He did his full-time doctorate in NIT Tiruchi on the area of power electronics application to power system. Presently, he is working as assistant professor in Department of Electrical and Electronic Engineering in NIT Silchar. Before joining NIT, Dr. Sreejith Sir worked as assistant professor in WIT Vellore. He published more than 50 journals and in referred international and conferences. And he is reviewer in IEEE, IET, elsewhere, Taylor and Francis, and Springer, and lot other international journals. He is serving as editor in board in few journals. He is given a member of lecture and a hands-on training on power electronics, power system, drives, facts, HVDC, smart grid. He is a member in board of studies in various institutes. He is guiding a number of BTech, MTech, and PhD scholars. His area of interest are power electronics, power system, renewable energy system, drives, smart grid, optimization techniques, packs, HVDC, and electric vehicles. So, in this section, Dr. Sreejith Sir is going to show his immense expert knowledge in the topic of solar energy in detail and integration to smart grid. Sreejith Sir, I invite you to continue with the lecture. Yes, sir.
Hello, sir. Am I audible?
Yes, sir. You are audible, sir.
1 second. Let me share the screen. 1 second.
Yes, sir. Sreejith sir, can you unmute yourself, sir?
Yeah. Is it visible?
Yes, sir.
Visible?
The PPT is visible. Yes.
Okay, well.
Yes.
Okay. So, audio clear and PPT visible, right? Okay.
Yes.
So, very good afternoon to all. It's my pleasure to meet you all here for this FDP. And first of all, let me thank the coordinators for inviting me for this FDP. And thanks for the esteemed faculty who has given introduction about me. So the topic which I'm going to deal today is solar energy basics and integration towards grid as well as smart grid. Okay. So what you're going to see now is that, okay. So we'll start with the basics of solar, because solar comes under renewable energy sources, right? So a small glance, what are renewable energy sources? Okay, so before going to renewable energy, then we need to know what are conventional energy sources we have. So we'll start with conventional. Then we'll move into renewable. Okay, and we have a lot of renewable energy sources. Out of that, we'll start with a PV system, solar photovoltaic system. Then we'll see the components. Okay. Then we'll see what are the conditions or what are things we need to keep in mind while we are going for the installation of a solar system. And finally, we'll see how to integrate this solar system to the grid. What are the things we need to keep it in mind? What are the types of inverter we need to do keep? All such things we'll see one by one. Okay. So first of all, let me start before going into renewable energy sources. Let's start with what is a non-renewable energy source. Okay. Of course, from the name itself, it's clear, right? Non-renewable. Okay. That means these sources, okay, they are all mostly natural sources only. Okay. But they are not renewable in nature. Sir, some audio is coming in between.
Sir, I think it's from your end, sir.
One. Hello. Yeah, it's okay now. Well. So actually, it's also a natural resource only. But the thing is that it cannot be remade or regrown. That's the thing. Okay. So that's why they are mainly called as non-renewable energy sources. Okay. So these are all the various sources of energy we have. This has both non-renewable as well as renewable. We have nuclear is there. See, these are the sources by which we are generating power. Okay. We have nuclear. We have coal, thermal power plants, we have nuclear power plants, we have wind, we have hydro, biomass, oil is there, solar is there. So these are all the various sources we have for generating power. Okay. This has both renewable as well as non-renewable. Okay. So the thing is that okay, everything goes fine, right? As of now, as a customer for electric power, I don't have any problem, right? Because I'm getting power whenever I'm switching on, it's there. Okay, sometimes I'll face power cut. That's all. As a customer, I don't have any issue with the existing power which I have, right? Whether it comes from non-renewable or whether it comes from the renewable, we don't have any issue. Okay, then where the actual issue is, that we'll see. Okay, so if you see the non-renewable energy sources, okay, so most of them are fossil fuels. Okay, so we have coal, we have oil, we have gas, all these things are fossil fuels. Okay, so the reason why they are called as fossil fuel is that they are formed from the fossilized remains of plants and animals, right? Millions of years before, not now or just 10 years or 20 years before, millions of years before, these plants and animals, okay, so they got deposited, cleared. These plants, they have been converted into coal, and the remainings of the animals or other living beings that have been converted into oil. This is the history we see in general. Okay, but the thing is that if we take this fossil fuel, out of 100%, 66% of the world's electric power is from fossil fuel only. Okay, if you take our country, India, around 69 or 68% of the power is from the thermal power station only. Only remaining will be from hydro, nuclear and all. But 69% of the power generation in our country is from fossil fuel. If you take the worldwide scenario, 66% of the power generation is from fossil fuel. And if you take the entire, let's see what we are seeing, 66% is just electric power. Okay, whereas electric power is not, I mean, it is not the only area where we are using fossil fuel. If you take your vehicle, okay, where you are using petrol or diesel or gas, if you go for a ship, if you go for aircrafts, everything they are using fossil fuels only. Okay, so fossil fuels are used for generating electric power. They are used for running the vehicles. Everywhere it is used. So on a whole, if you see, the 95% of the world's total energy is from fossil fuel. Either if you go for power generation or if you use as a fuel for your vehicle, if you take a total, 95% of them is from fossil fuel only. Okay, clear. Thing is that is it renewable? Clear. So the worst thing we have is that it is a non-renewable energy source. Okay, fossil fuels are non-renewable energy source. It doesn't mean that today I'll deposit all these things and tomorrow I'll get the fuel. It doesn't mean like that. Okay, millions of years before only those things got deposited. Now we are using it. Okay, and day by day we are depleting in a very fast manner. Clear? So you see how much power is generated now in our country. If you see world whole, how much power is generated from fossil fuel. See the vehicles, how many vehicles are running on the road. Everything is using petrol, diesel or gas. Only very rarely will have electric vehicles. So on a whole, if you see a single day itself, you can see how much fossil fuel is used. Okay. So if it is used in this manner, okay, soon those things will come to end. Okay, that is the thing. Okay, so this is a graph which shows the availability of fossil fuel. It has both coal, it has all coal, gas, oil, everything is there. Okay, if you are seeing coal, okay, this I think this color is coal. By 2081, by 2020, okay, somewhere the graph ends here. 2000, the entire coal in the world will go off. That's all. See, today I'm taking coal from here. Tomorrow I'll take from somewhere else. Day after tomorrow I'll go for another place. After that, finally, it will come to end in one day. Okay. It's not the only case with coal. If you go for oil also or gas also, everything will come to an end very soon. Okay. See, just think of a situation. If all these fuels are getting over on one fine day, how we'll be generating electric power? Okay. How we'll be running our vehicles? So everything comes to a standstill, right? So we need to find some alternate fuel for this one. Okay, that means these are non-renewable. They'll come to end soon. Okay, we can create it again and again. All such things. Okay, so we need to find some fuel which is renewable in nature, which is always available. Today I'll take from here. Tomorrow also I need to take from here. Day after tomorrow also it should be available here. That's what we want. As far as coal is concerned, today I'll take it here. It will get over. Tomorrow I'll go to another place. That's what happening, right? So we need to find an alternate fuel which is renewable and which is always available. Okay, so that is the first problem. Availability of fossil fuel itself is an issue now. Okay, see, 95% of the power, I mean, the energy is from fossil fuel only, but they are not they are unlimited, right? They are not renewable. If one find it can come to an end. Okay. So if they are available, see, the first thing which I have seen is that their availability. Okay, so they are not available, they are not renewable. Okay, but in case they are available, okay, using them itself is a big issue. Okay, availability is a problem. If they are available also, they'll create lots and lot of issues when you are using them. Okay, that you can see in day-to-day life, right? If you're using, see, for example, let me take a thermal power plant. Okay, because our country nearly 69% is from thermal power plant. So the worst thing which you can get from a fossil fuel is pollution. Okay, you can see, right, when you see the picture of a thermal power plant, okay, in the top near the chimney, you can see it's fully black. Clear? So the thing is that it will create lots and lots of pollution. Okay, it is not only with the power generation. If you go for your vehicles also, when it is running in a fossil fuel, you can see it's emitting a lot of gases. Okay, so pollution is the biggest problem when you go for fossil fuels. Okay, they'll run out eventually. Okay, but bad for environment. A lot of pollution will be there from fossil fuel. Okay, and if it's only pollution, I mean, only pollution means, I mean, we can't justify that. But along with that, a lot of other things will also come. Okay, that means when you're burning fossil fuel, it will be emitting a lot of gases. Clear? So that will be accumulated in the atmosphere. Okay, first thing is health hazard will be there. Okay, then you have global warming. That is the next biggest issue we have with fossil fuel. Then it is damaging the ozone layer. All such things are there. Okay, see, for example, if I'm taking a sun, okay, the sun radiation will come to earth, right, normally, and a few radiations are absorbed by the earth. A part of the radiation will penetrate into the earth, and some radiations will be reflected back by the earth, right? Since some radiations are absorbed by the earth, the temperature of the earth is okay, moderate, such that we can live. If it is not absorbing anything, means it will be very cool like some other planets. Okay, so since it is absorbing something, earth is warm, so that we can live nicely here. So what will happen is that when you're burning a lot of fossil fuels, all these gases will get accumulated in the atmosphere. It forms a layer. Okay, so whatever radiations they are reflected back by the earth, they won't go out. Again, they will be reflected back to the earth by this layer. So again, the temperature of the earth will increase. Generally, we'll call it as global warming. So usage of fossil fuel is the one of the reasons for this. Okay. Then one more thing is that since a lot of gases are getting accumulated in the atmosphere, when it rains, okay, it will dissolve in the water and come to earth as rain. Okay, so a lot of effects are there with fossil fuels. So we have pollution as an effect. Okay, then you have greenhouse effect, global warming. There is air with fossil fuel. Okay, as it rain, a lot of issues are there. So from the first one, we have seen availability as an issue. Okay, there we can understand that we need to find a solution by which the fuel is unlimited. That means we need to have something renewable, we can get it daily. But now you see effects are also there with This is fossil fuel. So now the new source which you are going to use, okay, should not create any pollution. Okay, there should not be any global warming, right? Okay, should not create, have acid rain. All such things should not be there with the fuel which you are going to use as an alternate. Okay, so this is what we need now. Okay, and so let's see, these are non-renewable energy sources. So then actually what is a renewable energy source? See, from the name itself it's clear, right? It's renewable. It can make it again, it can be remade again and again. Okay, they are natural resources. Okay, they'll be available always. Today I'm getting solar radiation here, tomorrow also I'll get it here, day after tomorrow also it will be there. We can't just think of a day there without sun, right? If sun is not there, then that's all clear. So it will be available always. And if you take wind also, as long as sun is there, wind will blow, right? So these are all renewable energy sources and they'll be available throughout. Okay, and they won't create any pollution. There is no global warming. There is no acid rain. Nothing will be there from the renewable energy sources. Okay, and there are a lot of renewable energies. I've just listed a few. There are a lot of renewable energy sources. Solar is there, geothermal is there, wind is there, biomass, hydro, a lot of renewable energy sources are there. But out of which mostly for power generation, that what is it? Wind and solar are considered. Okay, so even though you have a lot of things, okay, we'll be mostly concentrating on wind as well as solar. Okay, so in this presentation, let me concentrate only on solar. Okay, so solar is a renewable energy source. Okay, and if we see solar, okay, a lot of the things are there with our solar power conversion. Okay, that means one thing which will come to your mind when you're telling us solar power means normally you will think it's very costly, right? Because we need a solar panel, we need to have a lot of control, a lot of converters are needed. All such things are needed with solar, right? It's true that the cost of this is high initially, okay, long back. Okay, but now the cost of all these things came down. Okay, that means if I take 5 years before, uh, for example, if you want to go for a 1 megawatt of solar panel, it takes around 8 crores to have the installation. All such things includes 8 crores rupees. Okay, whereas now it came down to 3 to 4 crore. That means if you want to have a solar panel of 1 megawatt capacity, it came down to 3 to 4 crores. Still, as technology improves, this cost also will come down. Okay, so for better you want to go for green, all such things, this is one of the best solution. Okay, if you want to generate more power, if you want to go for green, clean energy and all, solar is one of the best solution. Okay, and if you see our country, okay, as far as the India is concerned, the government is giving a lot of incentives and a lot of other support for going for this green power. Okay, if you see by 2015, okay, so the total installed capacity of solar was around 3.7 gigawatt. That's all, 3.7 gigawatt, and by 2020 it is around 20. Hello.
Sir, hello, sir. Sir, whether sorry
Yes.
for interruption, sir. Whether
Yeah.
slides are in sliding mode, sir. I'm not able to see slides, sir.
Yeah, it's there.
Uh,
No, is it visible or?
it is in sliding. No, no, sir. The current slide is not available. Only the first slide only I am able to see, sir. Whether for my system it is problem or I'm having doubts, sir. For confirmation only.
1 second. It's a problem for all or only for you, sir? Let me check it. If anyone is having an issue, just you can tell. Then let me restart that again.
Yes, sir. We can only be able to see the first slides, but we can
The
able to
title
see.
slide.
Yes, sir. But the cursor is visible.
1 second. Once again. Whether this slide is visible now, the solar power.
No, sir. It is showing like ND. Now, yes, sir. Now you keep in slide mode, sir. Then it will be
Yeah,
slide
if
show.
this is visible, let me slide mode.
Yes, sir.
This
Yes,
is
sir. Now, that arrow is visible now, sir. Keep in slide show, sir. It will be.
okay. I think this is also visible, right?
Yes, sir. Yes.
Okay, I can tell the title fossil fuel effects. If it is visible, then I can go further.
Now we can see that solar power, sir. Solar power slide, which is already.
Not working.
Just make it at bottom of the slide. Some slideshow option is there, sir. Just click on that, sir.
Yeah, it's in slideshow only. Actually, I can give the slideshow. I'm just running in slideshow only. Let me do one thing, sir. Let me just 1 second. Let me reconnect it. I'll just go off and come 1 second.
Okay, sir. Okay. Thank you, sir.
So is it visible now?
Yes, sir.
Slide mode?
Fossil fuels.
Shall I continue? It is okay?
Yes, sir. It is fossil fuel effects. You can continue, sir.
Okay. Next slide is energy conversion. It's working?
Next slide is not visible, sir. Fossil fuels effects only it is visible.
Then it's only the slide which is before. Okay, let me change the presentation mode. So now it's not in presentation mode.
Okay.
Changes?
Now, yes, yes, sir. Yes, sir. You can proceed, sir. Now.
Okay for you because I don't know what technical error it is. If this is visible, then let me move to this like this. Okay.
Okay, sir. Okay, sir.
Okay. Well, oh, I crossed around 15 slides now. Okay. So yeah. Okay. So what are as far as our country is concerned, by 2030, it is expected that around 450 gigawatts of power will be from the renewable energy sources. Okay. So see how much impact is there from renewable energy sources right now. Okay. And for example, if I'm taking this renewable as well as fossil fuel, just I'm taking an example. If I want to generate 1 megawatt hour of power, okay, from a fossil fuel, okay, you can see it's emitting around 1,500 liters of carbon dioxide, and the temperature of the earth is increasing to 1.8 degrees centigrade. Okay. Whereas the same amount of power, if I am generating from a solar panel, okay, so there is no emission and there is no increase in temperature. See, initially we have seen the effect of fossil fuels, right? We have seen the effect of fossil fuel. So first thing we have seen is that we need to have a fuel which is renewable in nature. Now we can understand solar is renewable in nature. Okay. Then the second one we have seen the effect of fossil fuel. That means it is emitting a lot of gases. Okay. It's increasing the temperature. Now we can see there is no emission and there is no increase in temperature. So this is one of the fuel which is renewable and there is no emission and there is no global warming. Okay. So now I've arranged all these things. That means so power generation, where you can see solar is separate. Okay, whereas all the remaining people are on one side. So it has both renewable as well as non-renewable energy source. You can see coal is there, oil is there, gas is there, nuclear. Everyone is there on one side, whereas solar is there on other side. Okay, the difference is that if I'm taking a thermal power plant, okay, so we know how power is generated in a thermal power plant, right? We'll be having coal, okay, it is crushed, powdered and all it's done, then it is ignited, okay, so heat will be produced, that is used to boil water, okay, that is converted into steam will run a turbine, turbine will run a generator, we'll get electric power. So the source is a coal, whereas the output which I want is an electric power. In between, you can see a lot of power stages are there, and most of them are mechanical stages. Okay, so from the input coal to the output electric power, we have a lot of conversions. So lot of power loss will be there in between. Okay, so the output will be getting very less compared to how much input you are giving, right? So we have a lot of conversion stages, lot of losses will be there. So the efficiency will be very less here. Whereas if I'm taking a wind turbine also, even though it is a renewable energy source, if I'm taking wind turbine, you have wind, okay, then you'll be having blades. So the wind will strike on the blades. So the blade will rotate, okay. This is connected to a low speed shaft because the wind speed is very less, right? It's connected to a low speed shaft. Then you'll be having a gearbox which will change the speed ratio, Then you'll be having a high speed shaft because the speed is increased. Then after that, you'll be having a generator. Okay, that will from that you will get electric power. So again, if you see, even though this is a renewable energy source, we have a lot of power conversion stages in between. Okay, but if you see simply, if you take solar, okay, solar radiation will fall on the panel. Okay, it's directly converted into electric power. There is no intermediate stages when you go for a solar panel. Just the solar radiation is directly converted into electric power. But after that, we need some power converters, which is used for just changing the power level. Okay, but it's changing the voltage level. But it's okay because the efficiency of those converters will be always above 95. Okay, so that is not an issue. So this is a source by which the fuel is directly converted into electric power. That's why solar is separate, whereas all these people are coming on one side. This is the advantage with solar. Okay. Now, if you see how solar is converted into electric power. So if we take a solar cell, okay, just I'm telling only simple solar cell. Okay, so solar radiation will fall on the solar panel. Okay, so what will happen is that three things will happen when solar radiation is falling on the panel. Okay, so first thing, I mean, one is that some radiations will be absorbed by the solar panel. Okay, then there are some radiations which go, which will penetrate to the panel and will go. Okay, and there are some radiations which are reflected back by the solar panel. So three things: some radiations are absorbed, some radiations are reflected back, and some radiations penetrate into the panel and it will go. So even though three things are taking place and all the radiations are falling on the solar panel, the radiations which are absorbed, only the radiations which are absorbed are converted into electric power. Even though all entire radiations will come on your panel, only the absorbed radiations are converted into electric power. So with the efficiency of a solar panel is very, very less. It's always theoretically it will be less than 20 only. Because not all the radiations are converted. Only a part of the radiation is converted into electric power. Okay. And so this is a spectrum. Okay. I think I'm not sure whether I can see it fully or not. This is a solar spectrum. Okay. See, solar spectrum has a lot of radiations. Starting with the gamma, you have X-ray, you have ultraviolet, visible, infrared. Everyone will be there. Okay. So I'm not sure whether we can see it clearly or not. But let me tell you, if I take x-axis, okay, as the wavelength, it will start from the minimum wavelength and it will end at the maximum wavelength. Okay, so from the minimum wavelength, you will have gamma rays, then you will be having your X-rays, then you have ultraviolet, infrared, all such things. At the end, maximum wavelength, you will be having your microwaves, radio waves, and all. This is a spectrum. Okay, and most of these rays will come and fall on the solar panel. Okay, but why it is not converting everything? There is one specific reason for that. Why solar panel is not able to convert the entire radiation into electric power. If it is able to convert everything, means then it's okay, it's huge, right? Lot of power you'll get. Okay, so the thing is that, okay, as per Planck's law, okay, Planck he has given law, as per Planck's law, okay, so what he has told is that, okay, so the energy of the radiation is inversely proportional to the wavelength. Okay, that means longer wavelength radiation will have less energy, whereas shorter wavelength radiations will have more energy. Okay, so short wavelength means this side ultraviolet, okay, gamma rays, they are very short wavelength, they have more energy. Whereas when I come to another end of the spectrum, you have infrared, you have microwave, radio waves, all such things are there. Okay, they are having longer wavelength, but their energy is very, very less. Okay, so the energy is different with respect to the wavelength and it is inversely proportional to the wavelength. It doesn't mean that longer wavelength means more energy. As per his law, longer wavelength means less energy and shorter wavelength means more energy. Okay. So what will happen is that as far as a silicon cell is concerned, okay, as far as the silicon cell is concerned, okay, so it needs minimum energy to emit a photon, right? It needs minimum energy for generating electric power, okay. So the wavelength corresponding to that energy is 1110 nanometers, okay. So the wavelength or the energy needed, okay, for a particular, that wavelength is 1110 nanometers, okay. 1 second. Okay, nanometers. Okay, so I'll just show the spectrum now. Okay, see, this is a spectrum I have. Okay, it starts from 200 to 2200. So as per his law, okay, 1110 is the one which I need. Okay, so 1110, let it be on one side. Okay, so as per this law, if the wavelength is increasing, the energy will decrease. Okay, so if after 1110, if I go to 1200, 1300 and all, as the wavelength is increasing, the energy is very less. So after 1110, I can't go. 1110 is that maximum level then, because wavelength is increasing, energy is decreasing. So 1110 is the level I have now. Let me come below that. 1100, 1800, 900, 700, all these things are shorter wavelengths. They'll be having more energy. Okay. So they'll be having more energy. Okay. So now it's clear that shorter wavelengths are only used for producing electric power. Okay. Now let me start from the minimum wavelength. See, as far as the minimum wavelength is concerned, ultraviolet rays will come. But ultraviolet rays won't come fully to the earth, right? You have what is that in the top ozone layer. So ultraviolet rays won't fully come to the earth. Okay. One second, is the audio clear? Because I can't get any feedback in this one.
Yes, sir. Audio is clear.
Okay. So if you see the lower wavelength, ultraviolet, okay. So they have more energy as per Planck's law, but the thing is that they won't mostly come to the earth, right? So ultraviolet is also removed. So the only range is now from 400 to 1100. That's all. Because below 400, ultraviolet won't come to earth. Above 1100, they are having higher wavelength, but this is very less. Okay, their energy is very less. So only from 400 to 1100 only that is converted into electric power. Okay, and apart from this one, these rays will come, lot of losses will be there in the solar panel. If you treat it as a whole, only a very small percentage of the radiation is converted into electric power. If you have 0 to 2200 wavelength spectrum, out of that only 400 to 700 or 800 is only converted into electric power. That's the only thing, that radiations are only converted to electric power. So it's very less, right? So that's why the efficiency for if you have all radiations coming to the solar panel, but only a part of the radiation is converted into electric power. Okay, so the thing is that if you want to get more power, you need a huge area. Clear? That's the thing. Okay, so that's why it's converting very less radiation into electric power. This is specifically for silicon cell. Okay, but nowadays a lot of researchers are going in this area. They are adding a lot of impurities. They are changing the material. I mean, a lot of dopings are done such that they can improve the efficiency. Okay, we can change the material. Silicon is the one which are using, because germanium mostly we won't use. So in silicon, they're making some modification in silicon such that more radiations are converted into electric power. And nowadays they are going for these nanomaterials also, such that more incident radiations are converted into electric power, and they can increase the efficiency. Okay, if solar panel efficient, I mean, if the efficiency is about 95 or something, you need to understand that this is the efficiency of the system with the converter, right? Only if I take the solar panel, the efficiency is less than 20. Now it's going to 25 with a lot of coatings and a lot of other things. Okay. And the next one is, okay, I have a solar panel. It's understood that it will be, radiations will come on the panel. It will be falling on the panel. It's converted into electric power. Okay, that's all fine now. But the thing is that, okay, how to keep the solar panel? It's very simple if it is horizontal, right? No mountings, nothing is needed. Just simply we can put it in the floor, right? But as far as solar panel is concerned, the position is very important. Okay, we can't simply keep horizontal to the plane. Okay, if you see solar panel anywhere, if you see solar panel, they will be tilted. Okay, you can't see a solar panel which is put horizontal to the plane. Maybe for laboratory experiments, we'll keep horizontal in the roof and all. But as far as the practical installation is concerned, always it is tilted. Okay, so I'll tell you why it is tilted actually. Okay, and this is things which are taken from NIT Silchar, you can see solar panels are always tilted, but the angle in which it is tilted also will change. Okay. Okay. The thing is that if I'm taking Earth, okay, one second, let me project this slide. Okay. Sir, my this pointer visible, what I'm drawing is visible there?
Yes, pointer is visible, sir. Red color pointer.
What I'm drawing is visible? Ah, yeah, well, so I need that because what are slides I have, I need to draw. So let me assume that this is our Earth, okay? Assume that is round, okay? So in the top, I have a northern hemisphere. In the bottom, I have southern hemisphere. In between that, I have the equator, okay? All such things are there. These things you already studied in history, okay? Assume that our sun is here, radiation will be coming, okay? So if you see the radiation of the sun, okay, it will directly fall on the equator. It will directly fall on the equator, whereas it will fall in the northern hemisphere and southern hemisphere at some angles. Okay, if you see equator, it will directly fall on the equator. Okay, but if you see northern hemisphere and southern hemisphere, it will be falling at an angle, not exactly perpendicular, right? So if I keep a solar panel horizontally in the equator, okay, if I keep horizontally on the equator, no problem at all. Sunlight will directly fall on the solar panel. Okay, so the countries near the equator, you can see they'll be mostly horizontal. I mean, panels will be mostly horizontal. Whereas if you take northern hemisphere, that is where we are living, right? We are in northern hemisphere. If you keep the solar panel horizontal, it's horizontal. You can see only a part of the radiation will fall on your panel. Remaining radiations will go off. Okay, if put it horizontal, only a part of the radiation will fall or even parallel. Whereas if I take a southern hemisphere also, if I put horizontal to the plane, okay, only a part of the radiation will fall on your panel, okay, remaining will go off. Okay, so in order to avoid this, what they'll generally do is that, okay, considering this as our earth, this is north, this is south, this is sun. Okay, so they'll tilt it by some angle. Okay, sorry, I'll put it here. They'll tilt it by some angle such that solar radiation will directly fall like this. They'll tilt it with some angle such that the solar radiation will fall on this. Okay, so that is why the solar panels are tilted. If they are put in horizontal to the plane, in equator we don't have any problem. Solar radiation will directly fall on that. Whereas when you go for northern and southern hemisphere, if you are putting the panels in horizontal position, only a part of the radiation will fall on your panel. Okay, so the output will be very, very less. So we will be tilting it such that it will face the sun. That means you need to tilt like that such that it is directly facing the sun. Okay, so that is why the solar panels are tilted. Okay, that's why they are not horizontal. And from this one you can see, if I am in northern hemisphere, the tilting is towards south, just opposite. If I tilt to northwards, north means again the solar radiation will come and strike on the back of your panel. Okay, so since I am in northern hemisphere, you can see it is tilted towards south. Whereas if I am in southern hemisphere, it is tilted towards north. So if you see any solar panel in our country, it should be tilted towards south. Okay, if you are tilting towards north, means you won't get anything. Okay, very less output you will get. That's why the solar panels are tilted. Okay, yeah, and this tilting, okay, so that's the reason why the solar panels are always tilted. Okay, I mean, our country, it will be facing towards, since we are in north, they will be facing towards south. Okay, equator, it will be horizontal. Okay, so the angle at which it is tilted is called as a tilt angle. The angle at which it is tilted is called as a tilt angle. Okay, but if you see this angle also, angle in which it is tilted, it will change with respect to the country. It will change with respect to the state. If I take our country, I'll show you here. This is the scenario in our country. This is scenario in our country. Okay, see, it's divided into 4 zones. Okay, you can see zone 1. I have in the top. Okay, Jammu and Kashmir, Punjab, and all. See, that depends upon the latitude. Okay, if the tilt angle depends upon your latitude, their latitude is around 30 to 36. So the tilt angle is 30 to 36 degrees. Whereas if we see zone 4, because Andhra, Tamil Nadu, Karnataka, and all, if you see the latitude is just from 12 to 18 degrees, right? So the tilt angle will be that degrees. Okay, and I am in just Assam. So Assam will be coming in zone around zone 3 or something. Okay, it's around 12 to 24 degrees. See, it changes with countries, right? If when you go for each and every country, their latitude is different. So the angle which you are tilting the panel is different. If I come inside India also, each and every state you can see different tilt angle is there. I'm having a solar panel of certain radiation in Silchar, okay? The same solar panel, if you go to Chennai or if you come to Andhra, okay, then the tilt angle is different. Okay, so you can just understand tilt angle changes with country and changes with place also. Wherever the latitude is changing, tilt angle will also change. But it's very tough to go for a perfect value. So normally we will go for some 20 to 25 degrees approximately and we'll keep it. Okay, so this is a tilt angle. Okay, so it has to be done properly. Okay, so that's why when you go for lab purpose and all, if you put horizontal in the roof and all, if you take readings, means output will be a bit less compared to the normal. Okay, and the next one is, you can see this one. Okay, so tilt angle changes with respect to the country and the, I mean state and all. Again, this angle, another one is, if you see position of sun. See, always as you have studied, it will be going from east to west, right? East to west we have studied. Okay, but it depends upon the days. See, always it will start from the same source and destination. They are the same, but the angle in which it is traveling will also change. Okay, because you just from this diagram you can see in the December 21, its source and destination is the same, but the angle in which it is traveling is different. Again, June 21 is here in this diagram. The angle in which it is traveling is different. Okay, so these things are very important when you are going for the forecasting of all these solar panel. That means if you want to forecast the output of a solar panel, you need to know which is the location. That means because that location will give you the latitude, that latitude will give you the tilt angle. Okay, then in which day you are going to calculate, because each and every day the position of sun is changing. Here that you can see the angle at which the sun is moving will change with respect to days. Here it is given for December and June. You can see just difference is there angle. Okay, so this is also important when you're going to go when you want to calculate the position of, I mean when you want to forecast the output of a solar panel. Clear? And a lot of other things also you need. Okay, so that's why solar panel is tilted, and this angle depends upon the place. Even in various climate also the angle is different. Okay, this is how, but this is not specifically followed. You can see in winter the angle is different, in summer it is different, and in spring also it's different. Because in winter the angle of sun will be different, in summer it will be different, and in autumn, each and every season it will be different. So all these things has to be taken care when you want to go for solar panel. Okay, connection. Okay. Now let me see. Let me tell you what are the connections of solar panel. Okay. So if I'm taking a single solar cell, okay. So the thing is that the output will be just 0.5 to 0.6 volt. That's all for a single solar cell. I think it's very tough to go for any application with this much lower voltage, right? 0.5 to 0.6. It's very, very rare to find an application with this. Okay. So in order to increase the voltage level, as we know, right? If you want to increase the voltage level, we'll be connecting them in series. Okay. So we'll be connecting them in series. Okay. So when you're connecting those in series, we'll call it as a module. Okay, if you are connecting them in series, it's called as a module. Single solar cell has 0.5 to 0.6 volt only, but these voltage I can use it for any application. So in order to increase the voltage rating, I'll be connecting them in series. For example, if I connect around 70 cells in series, I'll get around 35 volt. Okay, if I'm connecting 72 means I'll get around 36 volt. Okay, so that is actually a module, but for certain applications, okay. Okay, clear. But if you want to go for a solar panel with the 200, 250 volt means again I need to connect these modules in series. Okay, depending upon your requirement. For example, I have a module with a 30 volt capacity means I'll connect 10 of these modules in series so that it will be 300 volt. So likewise, you'll be connecting them in series. It's called as a panel. So we'll start with the cell, connecting them in series is a module. Again, connect all these modules in series. It will be a panel. Okay. Now voltage is okay, perfect. Okay, but if you want to increase the current or if you want to increase the power rating, still I'll be connecting these panels in parallel. Okay, that is called as an array. Okay, so depending upon your requirement, solar cell is very tough to use. You can go for a module, or you can go for a panel, or you can go for an array. That depends upon your the application. Okay, so cell connecting in series module, modules connected in series is panel, panels connected in parallel is a array. Okay. This is the one, cell, module, panel, array. Okay, so depending upon your requirement, you can use any of them. Okay, now let me come to the connections characteristics. Okay, 1 second. Let me project only this one. Okay. Okay. So here, see, it's very tough to find ideal panels, right? It's even when you go for power electronics, if you're taking an SCR, it's very tough SCR or diode. We normally will study that it's very tough to find a device with same characteristics. Okay, slight difference will be there between the devices. Okay, one has 1.69 volt means other one will go 0.68 volt. Like this, differences will be there between the devices. You can find two devices with identical characteristics. But assuming that is an ideal panels, okay. So each one is having a voltage of 0.6 and current of 0.8. That's an assumption. Assuming they are ideal, okay. I have panels whose voltage is 0.6 and 0.8 current, okay. So if I am connecting them in parallel series, okay. If I am connecting them in series, I can get 1.2 volt. They are connected in series, but the current remains the same, okay. And if you are connecting them in parallel, okay, then voltage remains the same, but the current will increase from 0.8 to 1.6 because they are ideal. 0.8 plus 0.8, 1.6. Okay. Then if I connect these two in parallel, so this 1.6 will come and this 1.2 will come. Okay, so I have connected two in series, another two in series, then the entire ring in parallel. So the current and voltage they have been added finally. So 0.8 plus 0.8, 1.6 amps I will get, and 0.6 plus 0.6, 1.2 volt I will get. These are for ideal devices. This is how they are connected. Okay, depending upon the requirement, you can connect either them in parallel or you can connect them in series. Okay, that depends. Okay. Yeah. So this is a characteristics of a. I'm sorry, I was not able to project it, so it will be very small only. Okay. So this is the characteristics of a solar panel. Okay. So depending upon the irradiation, the output of the solar panel will change. It doesn't mean that from morning to night you will get the same output from the solar panel. It will be changing. That's why solar is intermittent in nature. Okay, depending upon the irradiation, depending upon the temperature, depending upon the climate, depending upon partial shading, everything will change the output of solar panel. Okay, so this is not circuit, spelling is different. Okay, see, depending upon the irradiation, the output of the solar panel will change. So morning the irradiation will be different, 10 o'clock it will be different, afternoon it will be more, again evening it will be different. So it will be changing with respect to time, right? So as irradiation is changing, you can see, so the standard is 1000, that's the first one. As irradiation is changing, you can see the output current is coming down. Okay, whereas the voltage is approximately the same. Whereas and one more thing, so whatever characteristics of a solar panel is given, when I'm going to buy some solar panel, they'll give the characteristics curve, right? But it is specified for certain conditions. That means they'll tell this graph is for 1000 watts per meter square radiation and 25-degree temperature. That's the applicable. I mean, this is applicable only for such conditions. If the irradiation is changed, the graph will change. If the temperature is changing, the graph will change. Okay. So this graph is for constant temperature, but the irradiation is changing. Whereas next one, the irradiation is constant, 1000 watts per meter square, whereas where temperature is changing. You can see here, okay, at 10 degrees centigrade, the maximum power is 53, whereas 70 degrees centigrade, it is 39. So we can see the voltage changing when it is temperature is changing. So the thing is that as your temperature is changing, I mean, if at all temperature is increasing, the output of the solar panel will come down. Okay, see, radiation will change the output and the temperature will also change the output. It doesn't mean that if it is very hot climate, will get more output. Okay, if it is very hot, the output will come down. Okay, so the temperature as well as the radiation will change the output. So it doesn't mean that if you go for a cool country, the output will be very less, because if more irradiation is there, more output you will get. Whereas if you go for a hot country, you can't tell that the output will be more, because if the temperature is increasing, the output will still come down. Okay, so these factors will surely change the output of a solar panel, temperature as well as the radiation. Okay, and this shows the curves. Okay, this shows the curves, IV as well as PV curves of a solar panel. Okay, So see, it's actually DC, right? Simply by multiplying voltage and current, I can get the power. Okay. So if you see the curve, okay, if you see the curve, for example, let me take this point. Okay, here some current is there and some voltage is there. Assume that the power which I am taking here is P1. Okay. So if I multiply the current and voltage here, I will get some power. Let it be P1. I'm taking another point. Okay. Let the power here be P2 because current is approximately the same whereas the voltage is increasing. So surely P2 will be more than P1. Okay. I am taking this point. Okay. Let it be P3. The current has slightly decreased whereas the voltage is still increasing. Right. So P3 will be surely more than the P2 and P1. Okay. So as power goes on increasing, right? Okay. Let me come to this level because from this it can be seen that as voltage is increasing, power is increasing. Let me come to the maximum power level here. Okay. Sorry, maximum voltage level here. I'm taking the voltage here and taking the current here. See, current has reduced by at least less than half of the total, but the voltage has increased. So the power I'll get is P4 here. Surely it will be less than P3. Clear? So it doesn't mean that as voltage is increasing, power will increase because current is coming down. Okay. So there will be only one point where if you're multiplying the voltage and current, power is maximum. See, P3 is more than P2, P2 is more than P1. Okay. Then P4 surely it will be less than P3. Like this it will go. Okay. So at only one point where only I can get the maximum power. It doesn't mean that when the current is maximum, I'll get the maximum power, or when the voltage is maximum, I'll get the maximum power. Some point in the curve, I'll get the maximum value. So as far as this graph is concerned, this is a point by which if we are multiplying the voltage and current, we will get the maximum power. So that point is called as maximum power point. That's a point at which you will get the maximum power. The point is called as maximum power point, and the current corresponding to that is called as IMP, and the voltage corresponding to that is called as VMP. So if you are using this panel at IMP and VMP, then you can operate it at the maximum power. Okay. So you want to track it, right? Because we don't know, because this graph is fixed. Okay. If only this graph is there, then I know this is a point I can operate at this point. But when irradiation is changing, this graph will change. When temperature is changing, this graph will change. So whatever changes I make, I need to track this point, right? If only this is the graph, means no need for tracking. One point I know that is fixed. Whereas with a slight change in radiation, this graph will change because we already seen that. With slight change in temperature also, this graph will change. Okay. So then I need to track what is the point where I'll get the maximum power. That is called as maximum power point tracking. Okay. You have a lot of techniques for maximum power point tracking. One second. Okay. So we have a lot of techniques for maximum power point tracking. We have perturb and observe method. Okay. Hill climbing. Under hill climbing, how P and O is there, incremental conductance is there, voltage method, current method. A lot of methods are there for tracking the maximum power. Even you can use a lot of optimization techniques also. You can use GA, you can use ABC, ACO, you can use papers. A lot of techniques are used. So only intention is I need to operate this panel at the maximum power. So that technique is called as maximum power point tracking. Okay. Yeah. So along with the solar panel, if I take a solar system, see a lot of components are there apart from the solar panel. One thing is called as a blocking diode. Okay, so why it is needed is that if I am taking any solar panel, okay, during daytime, assume that I have a lot of radiation, solar radiation is there. A solar panel will work, okay, it will be generating electric power that will charge your battery. But at what happens at night time? At night time, there won't be any solar input, right? Solar radiation won't be there. So the battery, your panels won't generate any power. Whereas your battery is charged now. So the potential across the battery is more than the potential across your panel. So what will happen is that current will start flowing from your battery back to the panel. Okay, clear? So reverse power flow will be there. So in order to avoid that, we will be putting a diode in series with the panel. Diode will conduct in only one direction, right? So during daytime, when solar panel is working, current will flow through the panel and through the diode to the battery. Whereas at night time, when battery if it is starting discharging also, you have a diode which is connected in opposite direction there. It will be always reverse bias, so it won't allow current to flow through the panel. So that's why they are called as blocking diodes. They block the reverse power flow. Okay. Else what will happen is that at night time current will start flowing from your battery to the panel back. Okay. In order to avoid that, we'll be having a blocking diode. Each and every panel will come like this with a blocking diode. Okay. And next one is you can see bypass diode. This is another diode. See, bypass diode means, see, for example, I have a lot of panels connected in series. Okay, we have seen that the output of the solar panel depends on irradiation and temperature. Okay, so there will be something called as partial shading. For if there is any dust over the panel, assume that I have 5 panels connected in series. Above one panel, lot of dust accumulation is there, or some trees are nearby, shadow of that is coming and falling on one panel. Then the output of that panel will be different compared to other panels, right? So that difference will make lot of current flow in a different way, and that will affect the operation of the panel. So under such circumstances, what we need to do is that we need to bypass that panel. Okay, so for that we have a diode which is connected in parallel with the panel, that is called as bypass diodes. Under such conditions, these power will flow, it is bypassed through that diode such that the panel is eliminated from the circuit. Okay, so such diodes are called as bypass diodes. So you can understand that the irradiation will change the output. Okay, temperature will change the output. If you have any shading, that will change the output. Dust accumulation, everything will change the output of a solar panel. That's why they are intermittent in nature. Okay, and so now let's come to the next one. Okay, so basics of PV panels is clear, right? How electric power is generated, why you want to tilt the solar panel, all such things are fair. Now it's working fine. Okay. Now, can we use this panel directly to the load? Because I have a solar panel. What I want just convert this solar radiation into electric power. I got electric power directly. So whether I can use it directly to the load, that's the next question. Because as far as our AC supply is concerned, 230 volt RMS is coming to a home, I can plug the device and I can use it. Okay. Same as that, I have a solar panel which is directly generating electric power, but whether I can connect directly to the load, that's the next question. Okay, I can directly connect it, because one thing I have seen, right, from morning to evening the output is changing with respect to time. Such things I can directly connect it to the load. Okay, so we need to go for some power electronic conversion inside, then only we can use it for our purpose. So simply solar panel, it's very tough to connect it. Okay, so we'll be using a lot of power conversion techniques inside such that it can be used for any application. Okay, so mostly it is used for making the things efficient and to interface as for power transfer. Okay, that means you are seeing the maximum power point tracking, right? In order to track the maximum power point, maximum power point, if you want to identify it, we need to track it. So for that we can use power converters. Okay, for power converters needed for that. Then see, the output of the solar panel will be fluctuating, right? Irradiation will change the output. Then your change in temperature will change the output. See, I have an application which needs constant voltage. I want to charge a battery for 6 to 10 volt. Okay. I can use this panel directly because with respect to the conditions, the output will change. Okay. Then I need to go for some DC to DC conversion there, such that whatever fluctuation is there in the input, output will be constant and I can charge the device. So I need a DC to DC conversion there. Okay. Then after that, okay, it's DC now. If I want to connect it to my AC appliances, because most of the appliances I have at home is AC, right? The input is AC, even though we are working. For example, if I'm taking this laptop, the output, things will be DC inside, whereas we have a charger which will do all the functions. So input is AC, I can give AC input only. Okay, so the thing is that then I need to convert this DC to AC, again I need an inverter. So now we have the concept of net metering, right? So for net metering also I need to go for inverter. So for if you have only DC load or if you have only a battery to charge, then it's okay. But whereas if you go for application more than that, I want to use it for my AC load, I want to give this power back to the grid, then I need an inverter. So there also power electronics will come into picture. Okay, then it's not very easy to do integrate with the grid. We need to go for synchronization. So everywhere, whatever you need to go for power conversion techniques. Okay, that's why power electronics is needed when you go for such kind of applications. Okay, so this is a curve, okay, which is a practical curve in the day of April. This is we took when I was working in the IT Vellore. You can see the output is changing with respect to time. Morning 6 o'clock it's there, evening 6 o'clock is there. In between, that is from early morning and midnight, there is no power from the panel, and you can see the output is fluctuating with respect to the time. Okay, we can't use it directly to our appliances. And if you see this one also, see this is a practical curve which we took. The same solar panel, the output is changing with respect to the seasons. Okay, same panel, you can see somewhere the output is different. See, the starting and ending will be approximately the same here. Whereas you can see the output here, the summer it is different, in autumn it is different, in wind it is different, and spring. Each season it is different. So can you guess of having such a power generation, okay, will change with respect to this radiation, whose output change with respect to the temperature, whose output change with respect to the angle, whose output change with respect to the dust accumulated on that, and whose output change with respect to the seasons. So if you want to integrate this to the grid, clear, so we need to make a lot of conversions there. We need to add a lot of things inside. Then only we can make it perfect and we can connect it in the load. Whereas when you go for a thermal power station, just give this output. I have this much coal, assume that there is no fault in the system. I'm giving this much coal, I can get this much output. It's fixed. If you don't have any fault or anything, okay, some losses, leave it. If you go for hydro, if this is the input, I can give this much output. Okay, but as far as the solar, you can't do anything because even though radiation is coming, we have a lot of things inside. Temperature, everything will change the output. Okay, so you need to have a lot of conversion technique inside that. Okay. And if you see a solar system, what we have seen till now is actually solar panel. Okay, but this is just a small, this is one part of solar system. Okay, clear? Just one part. You have a lot of other things if you wanted to use it for some application. Okay, clear? So solar panel around, if you take the entire system, around 40 to 50% of the total cost is for the solar panel. But apart from this panel, you have a lot of other stuffs inside your system. Okay, see what components I'm putting is a very for a big system. Okay, you have a solar array. Okay, solar array. Yeah, solar panel is there. Then you'll have a charge controller. Okay, charge controller is used to control the charging and discharging of your battery. Okay, because see, simply I can charge a battery and discharge it like this, right? We need to maintain the voltage. The battery should not go below this value. Those control has to be done, right? So for that I have a charge controller. Then if it is a very big system, then I need a protection. Isolator is needed, a fuse box, all such things are needed. Then battery is needed to store the power. Okay, because at night you don't have any solar power, right? So if you are using a standalone system, okay, then you won't be getting power from the grid, right? Then I need a battery backup. Without battery backup, daytime I'll get power, whereas night I don't have anything. Then inverter is needed, meter is needed, tracking is also needed. Okay, so all these components are needed when you go for a solar system. Okay, and this is one perfect example. It's just a simple example. I don't have much conversion techniques inside. Okay, so PV is there, a charge controller is there, and a DC load is there. Depending, and battery is there. Battery will charge at daytime. Power will come to the DC load directly. At night time, when you are not having power, battery will supply power to the grid. Okay, I'll just maximize this one. This is the simplest application of solar power. Okay. You can see here. This is one application. I think that came in newspaper. I think this is in Bangalore. Okay. They are using just a simple solar panel, and you can see you have a fan here. Okay. You can see you have a fan here. Okay. So that is operated from the solar panel. So this is a simple application of a solar system. Okay. Clear? But this is a normal one. We don't want to go for much conversion. Whereas when you want to go for a big system, then you need to go for a lot of conversions. Here, this is one. PV panel is there. You have DC to DC conversion is there with MPPT. See, MPPT can be used in DC to DC conversion or inversion. That depends upon your circuit. If I'm using a string inverter, okay, or if I'm using a central inverter, then I need to go for DC to DC MPPT in the inverter itself. Whereas when you go for micro inverter, or if I have a DC to DC converter inside, then I can go for MPPT in the DC to DC converter. So this MPPT can be either incorporated into the DC DC or inverter. Anywhere you can incorporate it. So this is a normal diagram of a solar system. Okay. So you have a DC to DC converter which is giving power to the DC load, and battery will charge from this one. Then you have an inverter through which you can supply power to the AC loads, as well as if you want to give to the grids also. This is work. Okay. This is the diagram. So this is a typical graph of a charge controller. Okay, so this has 4 limits they have given. Okay, so you know what is a charge controller, right? It is used to control the charging of and discharging of a battery. Without that, we can't do anything, right? Because battery is a bit costly. I need to charge it only to a certain level, and I can't discharge below a certain level, right? So all these things has to be controlled. It doesn't mean that whatever power I will get, I can charge the battery and keep it big. Right, it can charge only up to its capacity. and I have a fully charged battery, I can drain it fully so that I can utilize it. That also I can't do. So there are certain limit for charging and certain limit for discharging the battery. That is controlled by this charge controller. Okay, you can see here in the top. Okay, the first one, voltage regulation is there. That means that is the limit till which the battery is allowed to charge. So when the charge is up to that limit, this automatically this will cut off the battery from the circuit. Okay. Then the second limit you can see is at VRH, that is a hysteresis level. Okay. So if you see the hysteresis level, the thing is that I have connected this battery to a load. Okay. So battery capacity will come down, right? So when I have to connect it back to the charger, that is decided by this hysteresis level, I can fix this level. So when the capacity of the battery comes to that level, again it will automatically connect to the source if you have option to charge it. Okay. Then you can see the fourth one, LVZ, low voltage detection, okay, or detector. That means we can't make the battery to discharge to 0%, right? We can discharge only up to certain level. Okay, beyond that we can't discharge it. Okay, so that is given by this LVD. Okay, when the battery's capacity coming to this level, automatically it will disconnect the load. Okay, because below that the life of the battery will go. Okay, and LVDH is a hysteresis value. The thing is that battery is disconnected. Now battery will charge. When I can connect the load back to the battery, so that is given by the hysteresis. See, it is just an example of a charge controller graph that depends upon a charge controller, but all these functions are done by the charge controller. When it has to charge, when it has to discharge, how much it has to charge, how much it can be discharged, all such things are decided by the charge controller. Okay, right. So next one is tracking. I think this animation is visible to all. Okay. Okay. So when you go for a solar panel, okay, when you go for a solar panel, the thing is that solar panel is fixed. We have seen it is tilted by some angle and it is kept fixed as it is. It's not moving anywhere. Clear? It's fixed there. But you see the sun, it's not fixed. It will start from one direction and it will end in another direction, right? So sun is moving from one side to other side, whereas your panel is fixed, right? So what that happen is that when it is coming to the middle only, full radiation directly will fall on your solar panel. When it is in this direction or when it is on this direction, only a part of the radiation will fall on your solar panel. That means you won't get the maximum power from all such things. Okay, so I'm sure if this animation is working, you can see the top. The first one is a fixed panel, and you can see when the sun is coming in the middle only, you are getting the maximum power. Okay, so when sun is coming in the middle only, you are getting the maximum power. Okay, so below which you won't get the maximum. When sun is on other two directions, you won't get the maximum power. So what we need to do is that we need to just move the solar panel with respect to the sun. When sun is on one side, I need to keep the solar panel on another side. When sun is moving, the solar panel has to move along with that. Okay, then you can get the maximum power, right? So that is actually the tracking. So this tracking, you have two types. One is called as a single axis tracking, another one is called as two axis tracking. Okay, so the first one is without any tracking. The third one is single axis tracking. Single axis tracking means one direction only. It's east to west or west to east. When sun is slowly moving in the same direction, your panel will move. Okay, so that is single axis. Only one axis it can move. Okay, again it will come back to west to east. Again when sun is moving, it will go along with that. Two axis tracking is that it can go in any direction, west to east, north to south, anywhere it can move. The thing is that, see, sun is moving from one direction to another one, that is okay. But this angle depends upon your, what is that, day. Today it will move in one angle, tomorrow it will move in a different angle. So always I am moving from west to east means you won't get the maximum power again. So I need to exactly track in the angle where it is moving. So north to south, west to east, all such things has to be tracked. So that is done by two axis tracking. Okay, you can, if this animation is visible to you, you can see that with fixed panel the output is different. With single axis tracking the output is different. With two axis tracking also the output is different. We need to track it such that you can get the maximum power taken from the solar panel. Okay. I'm sorry to tell this because presentation mode is not coming correctly there, so I need to move like this only. Okay, and when you go for this solar panel, you have a lot of converters, right? Because I need to go for DC to DC converters, I need to go for inverters. So if I'm taking DC to DC converters, you can use any type of converters. Okay, so from the basic, if I want to reduce the voltage, I can go for buck converters. If I want to go for the increasing the voltage, I need to go for the boost converters. And if I want to have both the operations, then I can go for buck boost converters. Then a lot of new converters are there. You have a cuck regulator, you have a quadratic boost converter, you have loop converter. A lot of new converters are there. Okay, but most of the cases buck boost, right? But only difference is that, see, if you want to go only for stepping down, I can go for buck. If you want to go only for step up, I can go for boost. If both are needed, I can go for buck boost. So the advantage of buck boost is that I can get both, but the disadvantage of buck boost is that the range is limited. Because if I am using boost converter, see, theoretically 0 to maximum duty cycle is used only for boost operation. Whereas if you go for buck converter, the 0 to maximum duty cycle is only for the buck operation. Whereas when you go for buck boost converter, 0 to 50% one operation and 50 to 100% another operation. So the range is limited, right? Only half of the duty cycle I can use it for one purpose, another half I can use it for another purpose. The range is limited. Okay. So now let's come for inverters, because if you want to connect this solar panel to the AC load, or if I want to connect this to the grid, because if I'm having what is that grid tied inverter, okay, then I need to go for this. If there is a what is that on grid, okay, then I need to connect it to the grid, right? I can give power back to the grid also. Okay, so such things surely I need an inverter. Okay, if I'm taking inverter, there are three main categories of inverter. In between also one or two are there, but these are the main. Okay, so micro inverters, string inverter, and central inverter. Three types of inverters are there. If I'm taking micro inverter, each panel has its own inverter. Okay, that is the thing. Micro means each panel has its own inverter. Okay, so that you can see here, right? You can see each and every panel has a 111 inverter there, right? So we'll connect all these things together and I'll take the output at the end. Okay, so you can see this picture. Okay, you can see each panel has a DC to DC converter along with MPPT, then an inverter there. It is connected to the panel. They are merged and they are connected. But for low power applications, I can use it from 200 watts to 300 watt. I can use this one. Okay, but the thing is that the advantage of this one is that, okay, since each panel is having a DC to DC converter inverter, I can operate each panel in its maximum power point value, right? Because each panel has a converter inside, so MPPT corresponds to that panel. Okay, so that is the advantage. Okay, so for each panel I can get it in the maximum power. And if I want to increase the capacity, add one more panel, because panel will come with an inverter inside. I don't want to change the inverter here, right? If you want to increase the capacity, just add one more panel, because inverter is coming along with that only. So I don't want to change anything else. So that is the advantage of this one. So very small applications I can go for the micro inverter. Okay, so next one is micro. So it is the best MPPT capability, because for each panel I have an inverter, so you can easily do it, right? It can be used for maximum power point. And for very small scale systems, I can go for this topology, because each one has an inverter. Okay. Whereas when I go for a string inverter, I think it will be around 5 to 6 panels or 6 to 8 panels depending upon the journal papers. Okay, so only these many panels are connected and we'll have one inverter for everything. Okay, so one inverter for these many panels. Okay, all the outputs of these strings are connected together and it is given to the inverter. So the thing is that there I need lot of inverters. Here one inverter for these many panels. And if, for example, here it is 5 panel, I have one inverter. If I have 20 panels, for 5 panel, one inverter, remaining 5 panel, another inverter. So totally I have 4 inverters. The output will be connected to the grid. Okay. But here the thing is that, one thing is that you have 5 panels, right? But only one inverter is there. So whose maximum power point? That is the thing, because it can operate only one maximum power point, your device. Each panel will have its own maximum power points, right? Because they are not identical. Each one have their own maximum power points. Okay. So here it will operate only one maximum power point. It can be a maximum power point of panel 1 or it can be maximum power point of panel 2. It doesn't mean that that's a maximum power point of all panels, right? So that is the thing. Individually, I can't operate in the maximum power point. I can operate only in the one maximum power point. That's it. Okay. You can see here. Okay, so string of PV cells are there. Okay, they'll be connected. PV panels are connected together. Mostly 6 to 8 are connected together, and that is connected to the output. Okay, and you can see here. All right. So only the individual MPPT is not possible. Only for the panels it is there. Okay, so that is a string inverter. Okay, so normally for these things, right, small scale and medium scale, like rooftop panels and rooftop you are using, for that they will go for string inverters. Okay, whereas when you go for a central inverter, okay, for the entire string, everything will have only one inverter. Okay, so I think in this diagram you can see the left side, all three are there, and this one you can see the left side. For all, they'll be connected, strings are connected together, and for all the system you have only one inverter. That's it. Okay, so that is a central inverter, and you can see the capacity will be very high because for everything will have only one inverter. Okay, but the advantage is that you need only one inverter. Okay, so the cost compared to for each and every panel you need inverter, for 6 panels you need an inverter. Here for the entire system you need only one inverter. The cost is bit less. Okay, in this case, and the number of wiring all requires are very less because no such connections are needed. For first micro inverter, everything has one inverter. When you go for the next string, each set of 6 panels have one inverter. Here everything has only one inverter. Totally only one inverter. Okay, so the capacity is huge. But the problem is that if the inverter is failing, that's all, everything will go off. Whereas as far as micro is converted, one inverter fails means only the output of that will go. Whereas in case of string also there is a thing, one string will go. Whereas if you consider this central inverter, if the inverter fails, the total system will go. Okay, and one more thing is that, see, as far as micro inverter is concerned, for each panel I can operate in its maximum power point. Whereas when I go for string, 5 panels or 6 panels are connected together. For them, I can operate in the maximum power point. Okay, but here for the entire system, only one maximum power point. Okay, so you won't get the full output from all these things, right? Micro, you can get the entire output from all the panels. String also it's okay. For 6 panels, I can operate. But here for the entire system, I have only one inverter. So mostly I can't get the maximum output from all the panels. Okay, so that is the thing with the central inverter. When you go for a huge power generation system, central inverter is mostly preferred. Okay, 1 second. Let me have a cup of water. 1 second. Come back to this one. Okay, so as far as centralized topology, this is a thing. Okay, and now you have a lot of other things in this one. You see, when you go for power electronics, right? Now most of the few applications will go for multi-level inverters also, right? Initially we had a normal, and if you take a HVDC system, if you take fax devices, everywhere multi-level inverter is used, right? When you go for a normal 2-level inverter, the operation is different, and multi-level inverters has a lot of other advantages, right? So when you go for a 2-level inverter, the output voltage increasing is a bit tough. Okay, then a lot of harmonics are there. Okay, all such things are there. Whereas when you go for multi-level inverter, a lot of advantages are there. Okay, that means you can operate with a high voltage and power ratings. Okay, so you can add the number of levels, and again we can use it for any applications. Then, see, as far as power electronics is concerned, okay, when you go for high switching frequency, the advantage we get is that since it is high switching frequency, you'll be having only higher order harmonics. Okay, so the filtering is easy, and the effect of these harmonics will be very less. That normally you would have studied, right? Whereas the switching stress is increased because continuously it is switched, and the switching losses will also increase. Whereas the same with lower switching frequency itself, you can get all these advantages when you go for multi-level inverters. Okay, so the output waveform will be better. We can use it in low switching frequency, and depending upon the number of levels, the output will be approximately a sine wave. So all these advantages make multi-level inverters one of the best options for AAC system, power converter. Okay, so mostly for industrial applications, everywhere MLI is used. Now, even when you go for solar PO, also MLI is used. Okay, So there are a lot of configurations of their neutral point clamp is there. Okay. Then flying capacity is there, cascaded H bridge is there. All those lot of topologies there are in MLIs. Okay, model, multi-level, all such things. But when you see the references, I've seen few references. Most of the cases they are working at neutral point clamp and cascaded H bridge inverters. Okay, so instead of going for a normal inverter, because there's a lot of works are going on this one, various topologies, which topology will give a better output, how to connect them to the grid. A lot of works are going on. So instead of a normal inverter, you can go for multi-level inverter also when you go for a solar PV system. Okay. And when you go for a solar power, okay, you can have two options. One is off grid or standalone. Another one is on grid. Okay, or grid connected system. See, off grid means see it is off from the grid, so there is no grid connection. Only the solar panel and all those associated things will be there. So here what will happen is that during daytime we'll be having output from the solar panel. It will be connected, kept in the battery. It will be stored in the battery and it is connected to the load. At night time, what will happen is that when solar power is not available, whatever power we get it from the battery, it is given to the load. Okay, that is off grid or standalone, standing alone without any support of the grid. But with some option, you can go for a diesel generator also along with that, because we can predict it, right? Solar energy is stored in the battery, but if this capacity is not enough for you, okay, then I can go for one diesel also along with this. So this is off grid. It's off the grid. Okay. And another one is a on-grid system. On-grid means both the grid as well as solar panel will be connected here. Okay. So output I can take from the solar panel, and whenever the output from the solar panel is not available or it is more less than the demand which I have, then I can get power from the grid also. And another concept is that if it is more than the required level, I can give back to the grid. And this concept is called as what is that? Net metering. Okay. I'll just show you one example for net metering here. I think this one. Okay. So consider that one example. Consider that I have a connected load today. This timing I have a connected load of 2 kilowatt. Okay, assume that I have a connected load of 2 kilowatt. Okay, then I have, see, this is a grid connected system. Okay, since it is a grid connected system, I have both solar panel as well as the grid. Whenever it is needed, I can take power from the grid. Okay, so load is 2 kilowatt. Okay, assume that I have a solar panel with a 1.5. Now see. At this point, it is generating 1.5 kilowatt, because that depends upon the irradiation and time. So at this point, it's generating only 1.5 kilowatt. Okay. Now what will happen is that from the grid, I need to take 0.5 kilowatt. So I'm just putting an arrow down. It means that I'm taking power from the grid. Okay, so the load demand is 2 kilowatt. Okay, from the solar panel I am getting 1.5 kilowatt. Okay, so from the remaining from the grid I am taking the remaining 0.5 kilowatt. Okay, this is okay, perfect. Okay, now next condition, again the same load of, after some time I have 2 kilo, again the same 2 kilowatt load is there, but now the solar panel is generating 2.5 kilowatt. Okay, so solar panel is generating 2.5 kilowatt. Okay, so I can see from here this 0.5 kilowatt is extra, right? 0.5 kilowatt is extra in this case. Okay, so what I can do is that, see, it's a renewable energy source, right? See, more and more renewable energy sources are needed actually, because our government they are giving a lot of incentives. Everyone is telling to move towards the renewable energy sources. Now we see I need only 2 kilowatt. I have 2.5 kilowatt generated. Okay, why I want to waste it? Okay, so give back to the grid such that everyone can use it, right? Because grid needs a lot of power during peak demand period and all. It's very tough, right, to generate power. So I can give this 0.5 kilowatt back to the grid. Okay, clear? So if I am having excess power, I can give it back to the grid. Clear? So 2 kilowatt is needed. I have 2.5 kilowatt generation. So the remaining 0.5 I can give back to the grid. Okay. So the thing is that, so for example, at the end of the month, okay, so I have consumed some 100 kilowatt. Okay, I have consumed 100 kilowatt and I have given back some 60 kilowatt. Assume that through net meter. This concept is called as net metering. Okay, so at the end of the month, okay, see, some states have months for 2 bills, some states have month for bill for 1 month, some states have bill for 2 months. Assuming that at the end of the month I have consumed 100 kilowatt power, and through this solar extra power I gave back 60 kilowatt. So the net difference is 40 kilowatt. So I need to pay only for this 40 kilowatt. This concept is called as net metering concept. Okay, so if we have excess power, give back to the grid. So this is called as net metering concept. But it's not very simple. It's not easy to go for such things. Okay, the first one is that you need you can't use it a normal. You can use a normal meter here. You need bidirectional meters, because see, when you're taking power from the grid, current will flow in one direction. That means from the grid you are getting power. Whereas when you are injecting power back to the grid, current will flow in opposite direction. It is going to the grid, right? So there you need bidirectional meters, because it has to measure both. Okay, so the difference in that will be you need to pay to the grid. Okay, so a normal meter I can't use it for such things. We need to go for bidirectional meters. Okay. And another thing, it's very important that I can't use a normal inverter for this case. If it is a grid connected system, I can't use a normal inverter. See, for example, I have a UPS in my home. Okay, I have a UPS in my home. There I have a battery and I have an inverter. So whenever power is there, it will be giving from the AC supply. Whereas whenever power goes, battery will be discharging to the inverter through which I can get AC power. So the function of that inverter is to convert DC to AC and give to the grid, give to the load, right? Then you will have some relays which will switch over during power cut and all. That is okay. But the thing is that it will be designed in such a way that it will generate output maximum sine wave at the 230 volt RMS and 50 hertz. That's the thing. Apart from that, this inverter don't have any function, right? It will generate output, okay, 230 volt RMS. It will generate it. It will get with 50 hertz frequency. That's all, depending on the capacity of inverter. Yeah, so this inverter is giving power to the home, right? So here also you can think that, so the same function is done in here also, because the inverter is converting DC to AC and it is giving to the home. The same can be fed to the grid also, but the same inverter I can't connect it for this purpose, because see, if I want to feed power to the grid, okay, the first thing we need to do is that synchronize it. Because grid has a voltage, frequency, phase sequence, everything will be there in the grid, right? So first we need to synchronize it with the grid, then only we need to go for that. So that synchronization is very important, okay? So when you go for a normal inverter, there is no synchronization, nothing. It is, since there is no power, it is giving to the load. That's all it will do. Whereas when you go for such kind of things, we need to go for inverters with a lot of other functions. It has to synchronize with the grid, right? When grid voltage is reducing a little bit, the output has to be changed accordingly. If frequency is just slightly deviating, the output has to be changed accordingly. So such kind of inverters only I can use it for this purpose. That is grid tied inverters I need. Normal inverters I can't use it for this purpose, because synchronization is needed. Okay, whereas a normal inverter don't have the option for synchronization, whereas these inverters should have the option for synchronization. Only such things I can use it for the this net metering concept. Okay, so that's why simply if you think that a normal inverter which I have in your home can be used for this, means we can't use it. We need to use another inverter which has all these functions. Okay, now let me tell you one example. Okay, here this is taken from a paper. Okay, actually see, net metering and all, they are a bit complicated concepts. Okay, so assume that I have a thing like this. Okay, so I have a solar panel, I have a connected load, and I have a grid. Okay, so this is a grid tied inverter. Okay, grid tied inverter means it has the ability to synchronize with the grid. According to that, it will work. Yeah. Now, assuming that this solar panel is generating some 2.5 kilowatt, okay, power. It is coming through the panel here. Okay, so the load needs only 2 kilowatt of power. Okay, so what will happen? 2.5 kilowatt will come from the solar panel, and 2 kilowatt will go to the load. Okay, and another 0.5 kilowatt will go to the grid. This is what a normal net metering concept. Okay. Okay. So this will work perfect. This is a normal net metering concept. This will work perfect. Now, one condition. Let me tell you one condition. Consider that. Okay. the grid is off. Consider that the grid is off. Okay, that means, for example, if there is any maintenance in the grid, normally what they will do is that they will switch off the supply and they will do the maintenance. Okay, so during maintenance, what they will do, they will be simply working on the transformers, and they'll work on the transmission lines, all such things, the distribution lines, they'll do all such things. Okay, because they can understand that. Okay, they can understand that they have switched off the grid, so power has been switched off, they can safely work in that. Okay, but when this net metering concept is there in the picture, okay, see, the condition here is that whenever the power is more than the power load, I mean demand, okay, whenever the power generated by the solar panel is more than your demand, it can be given back to the grid. That is the concept here. Okay, there is no question of the maintenance of service station and all, nothing comes in it. Just compare it. If more than the demand is there, send back to the grid. That's what the concept here is. Consider a condition. Okay, some fault was there in the grid. They turned off the grid supply, and people are working on the transformers and lines. Okay, but that won't reflect here because this I have a rooftop, I have solar power. That's all. So now, if this 0.5 kilowatt goes to the grid, what will happen? That is a big thing, because grid is already off. Clear? People are working on transmission lines, distribution lines, and transformers. But this converter, what generally it will do when demand is, I mean, less than your generation, the excess power will be given to the grid. So when people are working on the grid, thinking that the power is off, this power is fed back to the grid. That will create a lot of problems in your grid, because safety is the biggest issue, because people are working in the lines thinking that the grid is off, but with net metering concept, the remaining power is going back to the grid now. Okay. Clear? That will create a lot of issues. So that is why whenever power is off, this net metering should not work. Because whenever power is off, if grid is in maintenance, then your net metering concept should not work. It should not send the excess power to the grid. Okay, so these are the property of your what is that, inverter. Where we go for a normal inverter, nothing will be there. This will has the property of all such things. It will synchronize it first, then send power to the grid. And what will happen when grid power is off? When grid power is off, okay, when grid power is off, okay, so you can see, right, there won't be any reference, zero reference frequency and zero reference voltage will come. If that condition means it has to automatically turn off and stop supplying power to the grid. Okay, so during power grid is, when grid is in off condition, okay, we can't think that it is giving power to the grid such that when grid is also failing, power will be there for all. When grid is off, this net metering concept is turned off. Okay, since inverter will automatically sense that the grid is off and it will turn off. Okay, so these are all are there with grid tied inverters. Okay, and one more thing I'll tell you. Okay, so I can't make it big. I'll just tell you that. Okay, this one. Okay, assume that, see, when you go for a lot of malls and all, okay, you can see a solar panel will be there. Then they have backup diesel generators and grid is there, right? See, consider further the case of your diesel generator. Okay, I have solar panel. Okay, and the grid. You know the concept. When power is more than the demand, it's given back to the grid. Now consider an example. Okay, I have a generation of the same 2 kilowatt, and I have a load of 1.5 kilowatt. See, consider that the grid is off now. Okay, when the grid is on, what will happen? It will go to the grid. If the grid is off, okay, so now this when the grid is off, generally what, when you go for a very big malls and all, diesel generator will automatically come into picture, right? When the grid is off, diesel generator will automatically come into the picture. Now this diesel generator is itself is a grid for this solar cell, right? Because it seems that supply is coming, right? What it will happen, remaining 0.5 will try to enter into your diesel generator. Clear? There, since grid is off, everything went fine. Now diesel generator is there. If this 0.5 kilowatt enters into the grid diesel generator, again it will create a lot of issues. Again, one thing is there. Clear? This has to get synchronized with the diesel generator, because that will get synchronized with your grid now. Since diesel generator is connected, now this inverter has to get synchronized with the diesel generator. And if excess power is there, then it will go to the diesel generator now. So we need to be much careful when you're going for such kind of things. A lot of solutions are there, a lot of papers are there for solution, giving solution for such kind of issues. If you need things in detail, you can go for these reference papers. Okay. Now, what we have seen till now, okay, what we have seen till now is just a power generation from PV. PV is there, it is converting into electric power. I have grids a lot of converters. It's given to the AC load, it's given to DC load, all such fine. Okay, but it doesn't mean that this PV is used only for electric power generation. There are a lot of other applications with PV panel. Okay, see whatever we have just did till now is just the conversion of that light. Okay, whatever light is coming from the solar, I mean sun, it is converted into electric power and we are using it. But doesn't mean that only light is coming. You have heat also, right? That can also be used for a lot of applications. Okay, so for example, the first one is a solar water heating. Okay, see as we know, right, when you go for a solar radiation solar panel, it is converting into electric power. One thing we can think keep in mind is that it is converted into electric power, and the same power I can use it for heating. Okay, I have a normal water heater in my home. What will happen? Power will be there. You have a heater coil will be there. It will get heated and water will boil or something. That's done. Whereas if I think of solar application, in general, we can think of two ways. The first one is I have a solar panel. That heat will be, light will fall on the solar panel. It will be converted into electric power. That I can use it for heating. But normally it's not used like that. Only the heat of the solar panel is utilized. So when you go for solar water heating, most of the cases it's not converted into electric power. Only the heat from the solar panel is used for heating the water. Okay, so that is one application. So it doesn't mean that for all the applications the solar radiation is converted into electric power and it is used. It's converted into electric powers and used for some applications, and in some applications the heat of the solar panel is directly utilized for the application. Okay, see solar water heating means you have a water heater in the rooftop, you have a lot of pipes there, sunlight will directly fall on that and it is converted into electric, it is converted into heat. Okay, then water will get heated up. Okay, so that is solar water heating. And if you go for solar distillation also, distillation means just purifying water. So what will happen? Again the same, so heat from the solar panel is utilized. Okay, so that will fall on that. You have a black body, it will absorb the heat, then water will boil, and when it is boiling, it will go up, then it is again converted into liquid. Like this the process will go on. Here also only the heat is used, not it is converted into electric power. Solar pumping, here solar electric power generation, that's what you have seen. Then you have air conditioning also. When you go for air conditioning, again the same concept. We can have solar power which is converted into light, which can be converted into electric power, and then you can use it for input to a solar, input to the air conditioning, or the heat from the solar panel is directly used because a lot of cycles are there to heat the ammonia mixer and all. So for heating it directly, you can use the heat from a solar panel and you can use it for a refrigeration purpose or air conditioning purpose. Okay, so it means that whatever output, either if it is, you can use the light for our purpose or I can use the heat for my purpose. So it can be used for anything. Anything can be used for an application. And in transportation also, transportation you can see, as you know, right, when you go for electric smart grid, right? So electric vehicle, plugged in electric vehicle, a lot of concept will be coming. Okay, and for this also we'll go for this solar panels. Because for example, see when you go for an electric vehicle, what the thing is that we need to reduce the usage of fossil fuel, right? Again, the same concept of this is coming there also, because all your vehicles are running either in petrol or diesel or gas. I need to reduce the usage of the fossil fuel. Okay, not only the vehicles are running on the road, if it is going on the farm, if you see aircraft, if you see ship, everything runs on fossil fuel only. So just reducing the usage of fossil fuel is the main intention we need. So what generally we'll go for electric vehicles. But if you're taking the electric vehicles, if it is charged from the grid, okay, so grid itself is most of the power is coming from the thermal only. Clear? So what we'll see, the vehicle is pollution free because you have battery, you have a motor will never create any emission, it's free of pollution. Whereas you're charging the battery from the grid, there a lot of pollution will be there, because there mostly we are going for this not renewable source only. So for such things also, we need to go for renewable energy source. If we take charging stations for electric vehicle, so if you go for the power, because charging station means you need power, right? That if you can generate all the power from the renewable energy source with solar, wind and all, then only we can eliminate all the issues with the existing vehicles. Because the main problem of existing vehicle is the pollution and availability of fuel. So if you want to avoid the pollution when you're converting into an electric vehicle, if the vehicle is charging from the grid, means still the pollution will increase on your grid side. Okay, so again for such kind of applications also we need to go for renewable energy source based power only. Your charging stations should have power which is taken from the renewable energy source. Then only we can avoid pollution and all. And another thing is that there are some applications where you have vehicles with rooftop solar panels. In cars, buses and all, if you see, you have solar panels in the roof of that. Okay, so power will come on that. I mean, light will fall on that. It is converted to electric power, and you can charge the battery and you can use it. Okay, so for transportation also we can use for these things. Okay, and when you go for a smart grid, okay, you know what is a smart grid, right? Because a lot of advantages are where the smart grid compared to the existing grid. Okay, when you go for smart grid, okay, you have a lot of components. You have a phasor measurement unit. You have a, what is that, communication system. You have cyber security. You have distributed generation. All such things. So it encourages the users to go for more and more renewable energy sources. Okay. So with with the existing grid, it's very tough to integrate all your renewable energy systems inside, right? Because see, with a normal grid, for net metering concept, it is very tough. Whereas when you go for smart grid, a lot of communication infrastructure with a lot of other things, it's very easy to install these things, integrate these things. Okay, so when you go for a smart grid, this distributed generation is a very important concept. Okay, because it's distributed generation, it's near the load side. When it is near the load side, the complexity will be avoided. We don't want to go for what is that, this much huge transmission of power. Transmission losses can be reduced, distribution losses can be reduced, and since it is much near to your load side, the voltage in which you are generating can be reduced. Because if it is coming from somewhere else, means I need to step up it and increase the voltage and need to transmit it. Whereas since it is much near to the load side, the voltage level can be very less. So it's very easy to integrate into the grid. Okay, so for all these applications, we need to go for renewable energy sources, and we have solar as well as wind. But I'm just taking about the solar. It can you go for wind also. Both the options are possible. But if you see solar or wind, sun is essential, because without sun, solar output won't be there, and without sun, you don't have wind also. Because see, uneven heating will make the wind to flow, right? So without sun, both of them won't work. Okay. And these are some applications where we have solar panels. You can see lights, street lights. We are using solar panels now because daytime your battery will charge from the solar panel and night will turn on. Okay, and you can see this is one, right? This is a Narmada Canal project. So as far as this is concerned, there's two options. One is that it will avoid the evaporation of water, and the second one is that it's used for generating electric power. Okay, and this is one airport, right, in Kochi, Nedimaseri airport, it seems. So full and full solar panel, right? Not even a single grid connection there. See, just started with the solar panel for small application. Now see, for the entire airport, it is powered by solar panel. So it's clean, green, and all. A lot of things are there with this. Okay, so solar is used for all such kinds of applications. And now we can see the capacity is initially started at some megawatt. Okay, now it is in gigawatt, and in 2030 we are expecting 450 gigawatt of total renewable energy into the grid, and by 2030 or 2040, 60% of the power generation will be from renewables. Like there's a lot of stuffs are there. Okay, but this area is not saturated. Lots and lots of works are going on in this area. Clear, if you see the solar panel, there itself a lot of work is going on how to improve the efficiency with respect to the material. Okay, and if you see converter, a lot of new topologies are there with reduce losses, reduce switches, how to incorporate MPPT. Then if you go for inverter, a lot of work is going on, grid tied inverter, all such things are there with battery charging. So a lot of work is there in each and every part of this one. Okay. Another one is that, see, everything is fine, but integrating this into the grid, okay, see, simply synchronization won't work. Synchronization means I have integrated into the grid, but there are a lot of problems with the source itself, right? Because solar power is. Hello? Hello? Okay. There is a lot of problems with integrating when you go for this one, right? See, for example, I can have, see, as in that there is no renewable connected to another grid. I have coal, I mean power plant, I have hydro power plant. They can easily do dispatch because they know what is the load, forecast load and all, they can have it. Okay. They know if I have a thermal power plant, if I give this much input, this is the output I can get. Now, if I go for a hydro, if I give this much input, this is the output I can get. So accordingly, they can go for dispatch. So assume that I am integrating a solar panel into the grid, right? So weather condition will change the output, irradiation will change the output, temperature is going to change the output, everything is going to change the output. It is intermittent in nature. So believing that you will get this much power from the solar panel, okay, if you go for a dispatch, when suddenly renewable energy output is reducing, means again I need to increase the power generation there. That will create a lot of issues. Okay, so it's very tough to balance the power when you go for such kind of thing. A lot of development in technology is needed for such things. Okay, and when you go for this one also, now a lot of power converters are coming inside. See, DC-DC converter, DC-DC inverter, a lot of things will come. When you go for power converters, the first thing which will come in your mind is harmonics. Okay, all such things again. When you go for maximum power point tracking, all such things are needed in this one. There's a lot of issues are there with integrations. Okay, and that's all from my side. Okay, so if you have any the slide is visible. If you have any clarification, you may ask now, or if say sorry for that, I am not able to project it. I think some network issue here. Okay, that's why I was not able to project it, because each slide I have a lot of diagrams and something I thought of writing also, but with this one I can't do anything. Okay, sorry for that. And if you have any queries, you may ask now, or still if you have any queries, feel free to put a message in my WhatsApp. I'll help you out, or I'll reply. Okay. Thank you, sir. Is up to the coordinator now.
Yes, participants, if you have any queries related to the topic today sir has discussed, you can unmute and ask the doubt. You can clarify your doubt. Yes, participants. Participants can unmute their mic and clarify their doubts regarding today's topic covered by Sreejith sir. Yes, sir. I don't think we have any doubt related to today's topic. Good afternoon, everyone. Sir, it's my immense pleasure to give vote of thanks to Dr. Sreejith Garu. Sir has covered few from basic topics to in detail topics on PV system and their integration. Sir covered topics like selection of fuel, which is environmental friendly for the power generation, and efficient generation of electrical power by considering different parameters like tilt angle, irradiation, location, etc. And then sir discussed basics of the PV system like series and parallel combination of a connection of a cell and their respective VI characteristics. And then sir discussed need for a controller, inverter and converter, and brief introduction on MPPT techniques that are available in the research field. And then sir classified inverters into three categories: micro inverter, series inverter and central inverter, and gave a detailed classification among these three inverters. And then sir gave the challenges that we are facing right now in integrating the PV system with the grid, with the wonderful examples like safety challenges, etc. And sir concluded his lecture with applications of PV system. So, sir, thank you, sir. In spite of your busy schedule, thank you, sir, for accepting our response to deliver a wonderful lecture on today's STTP program. Thank you, sir.
Okay, sir. Thank you very much. Thank you all.
Yes, I request the participant to fill the Google form which is going to be shared in the WhatsApp group. Participants are requested to fill the Google form which is going to be shared in the WhatsApp group. Participant can leave the session. We are going to continue the session 3, which is going to be tomorrow sharp at 10 a.m. Sharp at 10 a.m. Thank you, everyone.